So yeah, last year I found a bug in the glibc by complete accident. And I used the bug to compromise the PHP engine in two different ways. Sadly, we only have 30 minutes, so I will only talk about the first one, which is the easiest one, but probably the most useful one as well. No summary because we don't have time. No who am I either, we don't care. Discovery. So the most important part is what can we do with a file read primitive in PHP? That's the starting point. Well, obviously we can read a file, okay? So we can read etc password, it's already a pretty good bug. But since it's PHP, we can also use network protocols such as HTTP or FTP. That all works. So it's basically an SSRF as well. So it's pretty good. But it's even better because there are also other PHP-specific protocols that we can use, such as //, which lets you read inside the contents of a file archive. A file archive, for those who don't know, is basically the same as jar for Java. It stands for PHP archive. It will contain source files, resources, and also serialized metadata. And when you access the contents of a far file using // it will deserialize the metadata. So a very good attack starting from 2018, I think it was to, when you had a file read primitive in PHP, you would find a way to upload the far file on the server and then read the file using // and you would get arbitrary deserialization. And arbitrary deserialization using tools such as PHP GGC often means RCE. So that's a very good attack vector. But in PHP 8, the deserialization has been removed because they actually didn't use the serialized metadata. So it made absolutely no sense. But yeah. So starting from PHP 8, which came out 4 years ago, this attack vector is gone. So people have started to think about other attack vectors, and they are focused on PHP // filter, which allows you to apply transforms to a stream before it's returned to you. The idea is that you indicate a resource, such as a file or an HTTP resource or an FTP resource, everything that we've seen before, and then you apply a list of transforms onto it. A very simple example, say that we want to read etc password and we want to convert it to base64. To do this, we can read etc password and then convert it, or we can use a PHP filter string such as this one, which indicates a single filter, which is convert.base64 encode, and the resource as etc password. And what you get is the base64 encoded version of etc password. The nice thing about filter is that you can stack as many as you want. So you can have 1, 2, 3, 4, 5, even thousands if you want. Like there's no limit at all. So here I'm calling base64 encode twice, so I get a file that is base64 encoded twice. Okay, so obviously you can do other things than base64 encode. You can put your stream in uppercase using string.upper, or in lowercase with string.lower. You can do some very, very old cryptography with string.route13. Obviously don't use it, I don't know why it's there. And there's also a dchunk filter that we're going to talk a little bit more afterwards that lets you decode HTTP chunked encoding. And there's also a very interesting filter that allows you to convert from some charset X to a charset Y. And the name of the filter is convert.iconv.x.y. So a quick example for the last one. Say that you have a file in UTF-8 and you want to convert it to UTF-16. Well, you can just use this filter, so convert.iconv.utf8.utf16, and the conversion is made automatically, as you can see. Well, filters are really, really interesting as an attacker for many reasons. And I started studying them in last year. And what I wanted to check was whether or not we could use filters to add an arbitrary prefix, which had already been done by other attackers, but also an arbitrary suffix to a file. And the idea for this is in cases like this. So you have a file read primitive, which is nice, but right after, it passes your file into like using a JSON or XML or stuff like this. So if you try to read etc password, obviously it will not work because it's not JSON. And well, that kind of limits what you can do with your file read primitive. It's actually pretty bad now. But if you can add an arbitrary prefix and suffix using PHP filters onto any file, you can make any file look like any other file. And so you can make etc password look like JSON, and then your fire primitive now works, and it's like the best fire primitive that you can have, a simple fire primitive. And I managed to do that. The name of the tool is WrapWrap. It's on our blog. You can see the link on the bottom. But what we really care about today is when I started building the tool, I didn't have much idea of how filters worked in PHP. So I built a few brute force scripts to get an idea of what some conversion followed by some other conversion followed by some other conversion would do to a file. Okay? And after running my scripts for like a few hours, I actually got a crash. But it wasn't like a PHP error. It was a crash, like a real crash, like the program failed. And, well, I had been working with PHP for like 20 years, so I kind of felt like it was PHP's fault, but it wasn't. It was the fault of the glibc. And the reason for this is that when PHP does a character set conversion, it will use Iconv, which is an API of the glibc, to do the conversion. The way Iconv works is you call Iconv open with some input charset and some output charset to get a conversion object. And then you send to the function Iconv this conversion object with an input buffer with some size and an output buffer with some other size. And Iconv says that it will not read too many bytes in the input buffer and not write too many bytes in the output buffer. Otherwise, you have an out-of-bound read or an out-of-bound write, which is problematic. Well, it turns out that when you convert to ISO 2022 CNX, which is a Chinese character set that you probably never heard of, I didn't, well, it may sometimes fail to check the bounds before it issues some escape sequences. And the result for an attacker is that we may get an overflow from 1 to 3 bytes, but we don't really control the bytes that that the overflow consists of. We can get only one of the 6 values here. So we may have like $*H or $+I or $+J, etc., but that's only one of the 6 values. So it's a bug, but it's not that good. Just to give you an idea, those are the characters that may actually trigger the overflow. Those are Chinese characters. I have no idea what they mean, but yeah, they give you an overflow. So if we look at the vulnerability, we have a 1 to 3 bytes overflow, which is okay, I guess. We don't control the values, which is not that good. But in addition to this, we have lots of conditions to reach the bug, because we need to control the output charset for the conversion. It needs to be ISO 2022 CNX. We need to control part of the input buffer so that we can put in the Chinese characters that I was telling you about. And also, we need to have a suitable output buffer. If the output buffer is way too big compared to the input buffer, well, we will not be able to reach the end of it, and therefore we will not have the overflow that we want. And so I spent, I think, weeks looking for targets, and I couldn't find any. Like, I was really close with some really good targets, but in the end, it didn't work. So I was kind of frustrated, and I went back to PHP filters because I knew that I could crash them, because I got a crash without even trying. So the idea now is that, well, we have a fire rate primitive, and instead of having the standard impact of having a fire rate on an SSRF, we want a shell. We want remote code execution. So how do we do this? Well, to understand how we can do this, we need to understand parts of PHP, such as its heap. So the heap is the thing that does the allocations and the allocations. It's probably the simplest heap that I've ever seen, so don't worry, it will be like very easy to understand. So the heap is page-based. It has 512 pages that each consists of 4,096 bytes, so 1,000 in hexadecimal. Each page contains chunks of a very specific size. So in each page, you can have chunks of some size, but only one size. So for instance, in one execution, you will have page 10 that contains chunks of size 100. In page 11, you may have chunks of size 30. Page 12, you may have chunks of size, I don't know, like 400. But it's always one chunk size per page. And then for free chunks, PHP will hold a singly linked list for each chunk size. So there's a free list for chunks of size 8, a free list for chunks of size 16, 13, 32, etc., etc. The free lists are last in, first out. So that means that if I free a chunk of size 50 and I allocate one, it will be allocated at the same place. And if you do heap exploitation on the glibc, on the libc, sorry, it's very similar to tcache. but completely unlimited and without any protections. To give you a better idea of how this looks in memory, so say that we have the heap on the left with 512 pages, and say that in page 5 we have chunks of size 400. So that means that in page 5, as you can see in the middle, we have 4 chunks. In my example, I have chunk 1 that is allocated, chunk 3 that is allocated, and chunk 2 and 4 that are not, which means that they are in the free list for chunks of size 400. So at the beginning of each of these chunks, in the beginning of chunk 2 and the beginning of chunk 4, we have a pointer to the next free chunk. So in the first 8 bytes of chunk 2, I have a pointer to the next free chunk. So now what happens if I overflow of 1 byte from chunk 1? Well, obviously the 1 byte is going to go in chunk 2, and it will overwrite the least significant byte of the pointer that is contained in chunk 2. So now chunk 2, instead of pointing to the next free chunk, it points to, well, close to the next free chunk, but a little bit higher or a little bit lower, depending on where the pointer originally was pointing. Which means that we have altered some free list, which is a very good starting point to get code execution, even though it's only the beginning. So it looks very easy to exploit, right? Like the heap is really simple. No metadata, very simple to understand. Well, no protections at all. So why is it that you don't see remote binary exploits for PHP more, right? Because people always say that PHP is really bad security-wise. Why don't you see more remote binary exploits? Well, the main reason is that you have a one heap for one request policy in PHP. It's not a security measure, but every time you send an HTTP request, it will create a heap, allocate your HTTP parameters, so get, post, cookies, etc., into the heap. Then it will run the script, which means that it will compile the script that are used by your script, compile the script that are used by the script that are used by your script. So that's thousands of allocations on the allocations. And then it will run the script, and then it will destroy the heap entirely. So imagine that you have found a bug in the PHP engine. Well, the first thing that you need to do is find an application that will let you trigger the bug. Okay? That's already pretty hard. But in addition to this, during exactly the same script execution, you need to have the application use the bug. And the difference with other bugs is that generally you can send like several requests to set up your heap, and then a few more to trigger your bug, then you get your leak, and then you send a few more to reset up your heap, and then you send a few more to trigger the bug, and then you get your shell. Here, it's one request to get the leak, and one request to get the shell, which makes it really hard to exploit. You have to understand that in between the triggering of the bug and the usage of the bug, you cannot send anything else, like the script is running on itself. So it's basically a black box. You send it information, and you expect it to exploit itself. So yeah, the heap is simple to understand, but pretty hard to exploit. And now we can jump onto a PHP filter and understand how it works. Again, it's very simple. I've simplified it a lot, but as it stands, it's pretty simple. So we have a two-step process. The first, it will read the resource that you indicate as a stream, and then it will apply filters that you have indicated as well, one by one on the stream. So how is a stream represented? Well, generally, when you represent a stream, you will have a collection of buffers with some size that are linked together. So it's called buckets in PHP. So you have a first bucket, which contains part of the file. Then the second bucket that contains part of the file as well, and then the bucket that comes afterward, bucket 3, etc., etc. So for instance, if we read etc password, we may have the first 5 bytes of etc password in bucket 1, then 10 more bytes or 20 more bytes, and then a few more bytes in bucket 3, etc., etc. And so the list of buckets here, it's called a bucket brigade. Now that PHP has the bucket brigade, it can apply filters onto it. So we'll take the first filter, it will take the first bucket as well, and it will start applying it onto it. So it goes on, applies the first filter. So for instance, if it's base64 decode, it decodes the first bucket. Then it goes on to bucket 2, decodes it, then on to bucket 3, etc. So here you end up with a new bucket brigade, and you can apply the second filter onto it, and then the third one, and the fourth one, etc., up until you're done, and you are done processing your stream. So we want to convert a file read into RCE, and it doesn't look too hard now, because well, the file read is a file read already, so we can use it to read binaries. So we don't really have to get a leak, because we can read the libc to get symbols. We can read PHP to get other symbols. We can even check if the libc is patched by just reading it and looking in the code. We don't really care about ASLR and Pi, because we can read proc self maps. And a corollary to this is that the address of the PHP heap is known. We will see that it's useful afterwards. And also, it kind of feels like, since we have the bucket brigade technology and we can send as many filters as we want, it kind of feels like we can do arbitrary allocations and deallocations. We will see that it's not really the case, but it gives us, I mean, it makes us pretty happy about the exploitation. But at the same time, we're exploiting a web target, so we want a web exploit, right? We want something that we don't have to tune every time we send it to a new application. We want something that works against any application, against any PHP version, against any heap state, and we want an exploit that is completely reliable, and bonus point if it doesn't crash. So how do we do this? Well, we have a lot of problems ahead of us. The first one is that I was telling you about lots of buckets, you know, but when PHP reads a file or an HTTP resource or anything, it will only create one bucket with everything inside it. So if I read a TC password, it will create a single bucket with everything inside. If I read an HTTP resource, I get a single bucket with the whole HTTP response into it. And that makes exploitation pretty hard, because we cannot spray, we cannot pad the heap, we can't even use the altered free list that we create using the overflow. So it's doable, but it's really, really, really annoying. So we need to find a way to create, well, more buckets. And a way to do this is, well, the single one to do it, is zlibinflate, which will actually decompress the stream into several buckets. So obviously zlibinflate, what it does is it decompresses zlib compressed data. And the way it's implemented is that it will create a bucket with 8 pages, decompress into it. And if it's not big enough, instead of reallocating the bucket, it will create a new bucket to store the rest. And if it's not big enough, it creates a new one, etc. So what you get is lots of buckets, as many as you want, but they all have a really bad size of 8 pages, which is completely impractical for exploitation. So now we have as many buckets as we want, but the size is bad, so we need to resize them. A way to do so is to use the undocumented but pretty well-known dchunk filter. As I've said before, the dchunk filter, what it does is that it will decode a string, which is HTTP chunk to code it. And for those who don't know, it's, again, a very simple encoding where you have every time a size that is sent as ASCII X, and then some data, and then a size, and then some data, and then a size, and then some data, up until the point where you send the size of 0, which indicates the end of the buffer. As you can see here, the example will first read 8, which indicates that it will send 8 more bytes. Then it sends the 8 bytes. Then it sends 11, which indicates 17 more bytes because it's in hexadecimal, and it reads 17 more bytes, etc. And then it reads at the very end 0, which indicates the end of the stream. So now we have an easy way to resize our buckets, right? Like in bucket 1, if we wanted to have a size of 148, we write 148, new line, or data, new line, and then 0 to end the stream. We do the same in bucket 2. If we wanted to have a size of 100, we write 100, new line, data, new line, 0, new line, and so on. And we call dchunk, and it doesn't work. And the reason for this is that even though buckets are like parsed independently, well, separately, they are not parsed independently. So when it passes bucket 1, it reads the size, it reads the data, everything goes fine, and then it reads the size of 0, which indicates the end of the stream. So, well, the stream has ended, so it doesn't need to read bucket 2 or bucket 3 or bucket 4. Like, it just stops processing the stream. And so you end up with exactly the same situation as before, a single bucket with an arbitrary size. But we go back to square one, so it's useless. Luckily for us, we can do a very simple trick where in each bucket, we only write one chunk size and one data. And to do so, we just pad the size with like thousands of zeros, so that in bucket 1, we have the size of 148, then the data, and that's it. And then it jumps onto bucket 2. It processes it as well properly, and then goes on to bucket 3, bucket 4, etc. So at this point, with only 2 filters, we are able to convert a single bucket into as many buckets as we want with the size that we want. So we are getting closer to a good state to exploit. But it's not enough, because we actually need an exploit algorithm. As I was saying before, generally you have to send a few requests to set up your heap, then you send your requests to exploit, and then you need to send other requests to actually use the bug. And here we need to do this using a single PHP filter string. So we need to be able to have several steps in the exploit in which heap chunks get allocated and deallocated, but without sending anything else. So a way to do this is to actually think about only one chunk size and completely ignore the rest. Since the allocator is page-based, if I focus on one chunk size, for instance 100, chunks that are bigger, I'm not going to see in the exploitation because they are allocated somewhere else. And chunks that are smaller, it's the same, I'm not going to see them, they are somewhere else. So if I focus on one chunk size, resizing a chunk is kind of equivalent to allocating it or deallocating it. And now I just need a way to be able to resize buckets as the exploitation goes on without interacting with the script. And to do so, I built my buckets as Russian doors of chunked encoding, as you can see on the image on the left. And now, every time I call dchunk, every single of my buckets will have its size changed. So bucket 1 may have a size that is too big at the beginning, but then in step 2 it has a proper size. Then in step 3, the size that is too small. And so I can make buckets appear or disappear in the exploitation using this very simple system. And now I have basically everything I need. I can create chunks and I can deallocate them at will without interacting with the script. So now I just need to control some free list using my primitive, and it's pretty easy. I have a 1 byte overflow. I focus on chunks of size OX100, as I've said, and I want to overwrite next pointer entirely. So to do so, I first pad the heap, and I end up in step 1, where I have 3 free chunks, A, B, and C, with A as the head of the free list. So we have A that points to B that points to C, and I allocate these 3 chunks. We are in step 2, and then I free them, and we are in step 3. And now what we have is a reverse free list, where we have C that points to B that points to A. Then we get into step 4, and what we do is write at offset 48 in C an arbitrary pointer. Here I've written 11223344, but obviously you write whatever you want. And then you can allocate B and A as well and free everything. And we are in step 5. And in step 5, we are exactly in the same state as in step 1, but in C at offset 48, we have an arbitrary pointer. So now we overflow from chunk A. When we overflow from chunk A, we overwrite the pointer that is in B, okay? And so we displace it and we add 48 to its address. So now B was pointing to C, it's now pointing to C plus 48, which means that it points exactly where we've put our arbitrary pointer, and we can then allocate 3 more chunks. We allocate B, C plus 48, and then we allocate at an arbitrary address. So yeah, we're getting really close to exploitation now, but the only thing that we need to worry about is that PHP will willingly allocate anything at any address, but then it will try to free it. And if it tries to free it and it's not in the heap, well, where it should be, it will crash. So we need to go really fast. And in order to go really fast, I chose to overwrite a structure which is called zend heap, which is at the top of the PHP heap region, which we can find by reading proxf maps. Because it contains custom allocation functions, and I kind of did like the CTF trick where we replace the free function with system. And now when PHP tries to free something, it will actually call system onto it. So it gives us a way to execute a command. So yeah, quick demo. So I chose to focus on Cosmic Sting, which is a vulnerability that came out in June. It's an x6c pre-authentication on Magento. So obviously it allows you to read files. And without my exploit, the idea is that you can read any file you want on the system. So you can use the secrets that are located in some file, I don't remember the name, to create API keys. And so you have access to the admin API. But you don't have RCE. With my exploit, you straight up have RCE. So, yeah. On the left, you have a Magento website with absolutely nothing onto it. And on the bottom right, you have hopefully a shell at some point. And on top right, you have your exploit. Yay. Yeah. quickly, a few words about the exploit. It's on GitHub, so you can use it. It's not tailored to Magento, like you can use it for any fire primitive. So it works against any target. As long as you have a fire you use it and it works. It works from PHP 7+ to the current version, so that's 10 years of PHP covered with a single binary exploit, which I think is pretty cool. And also, you can use it against any PHP application. It can be like a Symfony website that is used by many, many people, or just an indie website that has been completely forgotten. It will work in any case. It's 100% reliable. I mean, almost. Also, the payload is really small because the first thing that we do is decompress it using zlibinflate, if you remember correctly. And that means that it's suitable for get parameters as well. Like the payload is not too big to send it using get, so that means that it can go anywhere. And in addition to this, you don't need to send anything else. You just send your PHP filter string and you get your shell. Like you don't need to send other PHP HTTP parameters to set up the heap or anything. Like everything is in a single PHP filter string. So yeah, basically it converts fire primitives into RCE in PHP. Yeah, I think I have time for a conclusion, right? So yeah, that's a new attack vector for PHP. Now, when you have a fire you have RCE, as long as the glibc is not patched, obviously. And that was also a way to attack PHP in many different ways, which I wasn't able to describe here because we don't really have time. I was able to get RCE on Roundcube, which is a famous webmail, but it was through direct calls to Iconv, so it's a completely different exploit. It's way harder, way more annoying. And hopefully, I'm hoping for targets, like other targets to come out if like people look into the bug. I actually spent, I think, 2 weeks looking for other targets. I couldn't find any, but maybe someone will be more like successful than I was. Well, I guess it would be discovered as time goes by. Sorry. And regarding timeline, I found the bug last year, but I couldn't exploit it straight up because I was working on something else. So I started at the beginning of 2024, reported it at the end of March, and the glibc security team were really, really amazing. They were competent, they were fast, and they were nice, which is pretty strange. Like usually, they're not even one of these qualities. And so they patched the bug, I think, in 1 week. And the bug was released after a 2-week embargo as CV 2024-2961. And so yeah, as I've said before, only 30 minutes, so I couldn't speak about lots of things. But if you're interested in this, there's our blog, ambionix.io/blog. There's the GitHub with every exploit, and there's my Twitter if you have questions. And that's it.